All right, good afternoon. My name is Chris Toogood. I have responsibility for products and services at Teradata. And I also have with me Fawad. He is a principal consultant here in EMEA inside of our big data practice. And what we're here to talk about today is really this idea about SQL in, on, and around Hadoop. You know, what does all that mean? Well, if you look at what's going on today, this is kind of interesting. This was the source of this was the Gartner Market Guide published in January, and this showed over 12 different SQL interfaces for Hadoop. And by the way, there are a lot more than are listed here. I mean, you've got Microsoft Polybase, IBM just announced another one, Fluid Query for their pure data system. What is it about SQL on Hadoop that is so interesting that everybody's getting into it? I mean, if you look at this list, you've got, customers that have put stuff together. I mean, Apache Drill, right? Apache Drill came from Google. It's the open source version of Dremel. You look at Presto. I mean, this is some work that Facebook did and brought it, into the market. You look at things like Impala, clearly what Cloudera is bringing in the market. The work around Tez and Stinger initiative on top of Hive. And then vendors, right? So Teradata and Teradata Query Grid, which certainly we'll talk about, as well as versions of IBM Big SQL, Oracle's Big Data SQL. What is the drive around everybody wanting to put SQL on top of Hadoop? And what we see with this is, I often characterize SQL as the language of business. Because what happens is, SQL is the foundation as a structured query language that most tools use to interact to get data. So all of your BI tools and all your visualization tools use this. So it becomes an important way to help get Hadoop more into the mainstream and to get it more pervasive within the organization. So what we want to talk about today is not to sit here and say, this one is better than that one, but to give you some different characterization about things you should think about when considering, SQL in, on, or around Hadoop. And they really break into these three categories. And the three categories, the first one is really completeness. And what I mean by completeness, one of those might be thinking about ANSI standards, right? What is the completeness of it? Do they support ANSI 88 or 92 or even beyond? What about things like ACID compliance? Do they support ACID compliance for transactional integrity? Do they have an optimizer? Right? I mean, just putting SQL on top of a file system doesn't make it a database. Do you have an optimizer? Is it a rules-based optimizer or is it a cost-based optimizer? So there's lots of things about completeness that you want to think about within SQL on top of Hadoop. The other thing you want to think about is performance. Performance of these different interfaces are significantly different. I mean, I'm sure we've all seen, we can improve performance of SQL on Hadoop by 1,000%. Well, it was coming from a pretty low baseline. And then the last one you need to think about is what is the architecture, right? What is the architecture around how is SQL on Hadoop built out? When I talk about SQL in Hadoop, it's really about Hive and how do you improve those characteristics. When you think about things like SQL on Hadoop, it's things like Impala. And when you think about things like SQL around Hadoop, it's really like Teradata Query Grid. And we'll talk about those different elements and components. So if you look at all the different architectural patterns around this, it really breaks into the four of these over here on the right-hand side of this screen. So the first one is, RDBMS on top of Hadoop. And I'll go into each of these, but basically some vendors have said, I'm just going to take my database and I'm going to put it on top of Hadoop and then use the HDFS file system underneath it. So that's one kind of design pattern for SQL on Hadoop. Another one is put the query engine itself, not the full database, but put the query engine itself really to be able to read HDFS files. And then the third approach here is really more of an orchestration approach, right? Where you have a relational data structure orchestrating queries and being able to push queries into Hadoop and then bring them back and join them together. And then the fourth one of these is really all about more of a virtualization layer, right, where you're doing true federation, not just with Hadoop, but with other relational structures and even other data engines within the overall enterprise. So why is this such a big deal? Well, part of the big issue that we've seen in the marketplace is when we were with Hadoop 1.0, and basically that foundation was HDFS and MapReduce, it was really good for doing programmatic type processing. But the problem with MapReduce is every time you did a map and a reduce function, it would go to I/O, it would go to the drives, it would drive a big drive within latency in terms of that delivering the result set back to the user. So a lot of people said, we need to get SQL on top of Hadoop, and we need to bypass, the MapReduce layer, because MapReduce doesn't give me really the interactivity for being able to do all of that different query processing. It's really more, focused very specifically around batch processing. Now, the good thing about MapReduce is it provided you that full flexibility. I mean, you could do anything you wanted against any of the data because you were fundamentally just programming that within that paradigm. So then came along this idea about, okay, let's do SQL on Hadoop. So the idea in the first design pattern here is the RDBMS on top of a Hadoop cluster. An example of this is what Pivotal Hawk has done. There's some good things to this. Like I said, it has the complete relational structure. The negative things potentially are that you're using a proprietary data dictionary. You're not sharing a lot of that core data across the entire cluster that others can have access to it. Some of these deployments are not Yarn enabled, right? So you're really taking over the complete cluster. Fundamentally, they've taken the relational data structure from underneath it and just put in HDFS. And so the data itself is really not portable to really be read by a lot of other engines within the infrastructure and architecture. The other thing is from a query processing on Hadoop, right? This is about the query engine, right? Not just taking the entire database structure, but the query engine itself, and then putting it on top of HDFS. Some examples of this are Cloudera Impala. IBM Big SQL is another example of this. The good news of this is quite often they use the standard data dictionary, right? The standard metadata within Hive, leveraging HCatalog, leveraging the ability to look at all kinds of different data formats within HDFS, ORC files. Some of the data types might be limited. You also need to be very careful about how complete is the SQL itself. We've done some benchmarks with Impala, and for things it does very well, it really does well, but it doesn't hit a complete complement of the entire suite. As an example, if you looked at a TPC benchmark, there was about 20-30% of the queries it just wouldn't handle. But the ones it did handle, it did really well compared to other engines within this space. So especially in this place, you have different query engines that mature at very different levels. Some of the stuff within the IBM Big SQL environment, they talked about taking some of the DB2 code and bringing it forward. The IBM Big SQL is really, the centricity of it is around Hadoop first, but has some additional maturity over what we see from Cloudera and Impala, Cloudera Impala's implementation. Then the third really design pattern here is this idea about the RDBMS orchestrating the queries, really with remote access to what's going on within Hadoop and with Hive. And the example here is what we do, which is Teradata Query Grid. There are a number of other vendors that do similar technologies. As I mentioned before, Fluid Data, Fluid Query just came out from IBM, very similar thing with their pure data structure. Oracle's, Big Data SQL is similar. But there's some things you have to look for here too. A lot of times what happens is if you're not doing dynamic correlation to the metadata, you can get the different environments out of sync. So you could change something within Hadoop, doesn't get changed in the relational structure, and then you're out of sync within that environment. So you want to be able to dynamically read the metadata and HDFS, and especially HCatalog. The other thing that you want to be cognizant of is thinking about the degrees of parallelism that happen between the RDBMS and the Hadoop cluster. As an example, with Teradata Query Grid, we literally map every single AMP to every single node within the Hadoop cluster, so you get complete parallelism, which drives very high performance, and you put it all on top of an InfiniBand connection across the different elements, and the systems act as if they're one. I mean, you're literally able to process terabytes of data within seconds as part of that. The other thing that happens here quite often is your SQL language is very good, right? Because the compatibility is very high because of the maturity of the SQL engines that were part of those relational data structures. And then the other nice thing is a lot of portability within the Hadoop data structures, because anything can access that data. There's nothing that you're doing to go in and really impact and take over the entire environment. As an example, with Teradata Query Grid, we actually push down processing into Hive, and then Hive is Yarn enabled, so everything that goes on within the Hadoop cluster can be leveraged. Other technologies that we've seen, like Oracle, Big Data SQL, it's very proprietary in nature in that you can access the HDFS as a south side within it, but it's only doing basic filtering. It's not doing full processing within the engine. So you just have to look at different elements and components around that. The fourth component here is really around query processing on Hadoop from a virtualization layer. And this is really pretty standard virtualization across anything that we've done within our information architectures. A great example of this is what was previously known as Composite, but is now owned by Cisco in terms of their data virtualization platform. The beauty of this in terms of this foundation is standard data dictionary, can use multiple different files. One of the challenges you'll see here, though, is really some performance. Because you're not playing the performance and processing where it lies, you're bringing stuff into a virtualized server and then processing it. So again, you just have to be cognizant about what are all the different components around completeness of the queries, what's the performance, as well as what's the different kinds of architecture that are part of it. What we see from a Teradata perspective is really this idea about moving from single platform to this logical data warehouse. And this is really Gartner's chart. I mean, a few years ago, it was all about single repository and relational data only. Now we believe that there's not one single technology that can do everything. I mean, you've got NoSQL engines out there. You've got MongoDB. You've got text engines. You've got graph engines. You've got so many different analytic types and functions that you want to be able to orchestrate in a transparent way across all of these different types of functions. So what we look at from a Teradata Query Grid perspective is really about creating this idea of a data and analytic fabric across all of your disparate type solutions within your enterprise. And in this way, you can really select what kind of data type are you looking for, what are the analytic engines that you want to function and leverage, what's your economic options, right? Obviously, storing data within HDFS is cheaper than storing it within relational structure. And then how do you want to leverage this? You might want to have different characteristics that execute very specifically based upon different CPU profiles or different characteristics around how much I/O is being brought back into the system. So with Query Grid, one of the things that we do is we really manage this foundation of having a very flexible architecture which doesn't just support Teradata to Hadoop, it also supports Teradata to Oracle, it supports Teradata to Teradata, it supports Teradata to MongoDB, and it supports Teradata to Aster, all within the same kind of Query Grid framework, so it's very flexible. When you're looking at different SQL and Hadoop options, you need to be careful because some of them are very proprietary in nature, and you want to make sure that it's really open and it can support not just that vendor's distribution, but multiple different distributions of Hadoop. As an example, we support CDH with Cloudera, we support Hortonworks, we also support MapR as part of this overall infrastructure. So just to give you an example about how this could work within the environment, let's say that you have lots of business users that are hitting the database, the Teradata data warehouse. And they're basically using that transaction level data to understand who are their customers that have high value, right? High lifetime value within that architecture. And that's data that's in the Teradata database. It's been there for a long time. The users are used to getting access to that data. But one of the things that they want to be able to transact against is understand, well, what's going on within this customer that has lifetime value in terms of their overall sentiment. Right? What's going on within their web behavior, what's going on within their social data. So how can I take those guys that have high business value and in context of just the people that I'm trying to query, go off and get sentiment information from within Hadoop. And what happens within QueryGrid is we open up dynamically, we push through, we look at each catalog, we understand where the data is, and then we push out parallel pipes to do one of two things. One, either grab the data, bring it into memory for processing the query, and then disbanding it, or we can persist it, or the other thing we can do is we push it down into the Hadoop infrastructure to process it where it lies. So we process it there, it performs there, get the result sets, and then bring it back up into Teradata. In this example, we understand who are the customers that have high business value, what's the sentiment of the customer. And then once we get that data, we can also then say, well, let me go over to the Aster platform and look at running a graph analytic. And let me execute that graph analytic to understand the sphere of this individual in terms of their sentiment and who else are they going to upset across multiple nodes within a graph structure. And so you're able to leverage different analytic functions all within a tight data and analytic fabric. So if you look at the way that QueryGrid's really positioned, is it's all about optimizing and simplifying all of these different disparate infrastructures. It's about being able to process and leverage the right technology to do the right job at the right time. And it's all about being able to minimize data movement, because data movement has no real value in overall processing, as well as minimize data duplication. So leverage the technology and the data at the point in processing where it's best allocated. So fundamentally, here's some of the core characteristics of it. I mean, it's parallel, high, bidirectional movement, push-down processing, like I said, native analytics, easy configuration, really simplified server grammar, which I'll have Fawad share with you. And then there's also an adaptive optimizer, which starts to extend the value proposition. I just want to give you an example of one of our customers. This is Shutterfly. I imagine a lot of you know Shutterfly. Shutterfly does about $400 million a year. They were growing at about 16% per year, but they were struggling with their Oracle infrastructure. So they came in and they got a Teradata data warehouse, and they bought a Hadoop cluster from us along with QueryGrid. Because one of the things they wanted to do is they wanted to capture all of the JSON objects from all of the different pictures. And every picture that they capture literally has like 100 different variables. I mean, it's got geolocation, it's got exposure, it's got time of day, it's got so much data about the picture, and they wanted to capture that information and start understanding behavioral characteristics against that. But it didn't make sense to model all that data and put it in the Teradata data warehouse. So they literally were able to push a query through QueryGrid into Teradata, go down to a billion-row table inside of Hortonworks, process the data, bring back 10 million rows back into Teradata, join it together, and that whole thing took about 6 seconds. Because of the high-speed parallel nature of the execution, it's very fast and very rapid. So what I'd like to do now is turn it over to Fawad and have him come up and talk about some of the syntax within it and give you some other use case examples that we've been working on. Fawad?
Thank you. All right. Thanks, Chris. So I'd like to take you through the syntax. So as you can see, it is a very familiar SQL syntax. One of the key things that you will notice is this @ sign and then the word Hadoop. So that is a new database object introduced in the Teradata database, which is called a foreign server. So that is the server which basically hides all the credential details, and it is managed by the DBA. So the DBA can provide all the libraries, and all the details are hidden. The username and password can be provided over there. And all you have to do is, if you have a Hive table name, my table, so you, in order to just, if you want to do a select of that table, you simply would say select static from my table at Hadoop. That's it. That is the complete syntax that will make the execution work. But the one that is happening right now is, it's slightly different. I'll go through it in a bit. So Chris talked about that, QueryGrid is a generic interface. It can go into multiple different technologies, and Hadoop is one of them. So it supports Hadoop, NoSQL. It can actually connect into SAS, R, Python, and other scripting grids as well. So what is happening in this query is, you see that keyword foreign table. So, and then you have this query in red. So the query in red is actually, in this case, the syntax of Hive. So what happens is, once you submit this query, the Teradata optimizer does not parse this query, and this query is simply passed down to the remote system, which is defined by the foreign server Hadoop. This could be, in the case of MongoDB or in case of any other grid, this could be a script, any R script, a Python script, and that would not be parsed by the SQL engine, just pushed down, and the processing would take place on the remote side, and the result set would be brought back to Teradata for further processing. And of course, the predicate pushdown and all other capabilities are also provided. In this case, what you would have is, you have a base table of Teradata TD_transactions, which could be a large table in there, and then you have transaction history, which could be much longer. So what you could have using this kind of syntax is, use the detailed data in Hadoop, use it for aggregation, and bring the summaries back, because as Chris said, it is very important that we are not, just because we can move lots of data, we start moving lots of data. So it's important to have high concurrency and high capability within the infrastructure, that we push down the processing as much as we can and bring as minimal amount of information to Teradata for processing. This is a key point of the execution. So with all these processing engines, it is very important that how is the optimizer of the initiating system managing those requests. So people are working on a cross-platform query optimizer, and what I would call this is really the first step towards building a full cross-platform optimizer. So what will happen in this one is, so if I write a simple query, select static from the local Teradata table, where column is equal to select max date from a Hadoop table. So what happened would in this case is, the optimizer will take out the query fragment, which is running on the remote side, execute that query alone on the Hadoop side, return the constant, rewrite the query, and if there is any indexing or partition elimination that can be possible on the Teradata side, that query would be rewritten and then executed. In this way, the optimization of the queries can also be done on the data that is returned from the remote queries. So which can be very, very powerful if used in the right manner. If you talk about the way the system does this execution, so for those of you who are not familiar with the Teradata system, so Teradata is also an MPP system. So it has the gateway into the Teradata system is called the parsing engine, which has the similar role as the master node or name node on the Hadoop side. And then the unit of parallelism within the database is called AMP, which is asynchronous multiprocessor, and it is the equivalent of the data node. But the main difference is that each unit of parallelism and the parsing engines within the database is virtualized. So when a query is submitted to the Teradata engine, the parsing engine makes a request to the HCatalog service running on the Hadoop system to share the metadata split information. So that split information is captured from the HCatalog service, sent back to the parsing engine, and the handshake takes place. So based on that, so in this case, we have 8 amps on the Teradata side and 8 splits on the Hadoop side. So once that metadata split metadata information goes back to the parsing engine asks each amp to make a direct connection to each of the data nodes where the split is located. So in this case, there would be 8 parallel sessions initiated, and this would be a parallel-to-parallel transfer. So the performance of this query is not just dependent on the network in between. The bigger the cluster on both sides, you will get significantly better performance on the query execution. The advantages of Query Grid is, it supports multiple different technologies. It has a generalized architecture, supports varying types of technologies at Hadoop. It supports Hadoop, all different distribution. It does not require any daemon process running on the remote Hadoop distribution, which allows us to connect to any systems out of the box without installing any daemon. It extends the integrated data warehouse, and you are able to combine the data from the data lake and the integrated data warehouse data in a much more seamless fashion. And using the predicate pushdowns and the function shipping, you can actually reduce the data movement and do the processing where the data is residing. If you talk about why this is important, so if you go back to the early 90s, so it was about getting some data very, very fast, building departmental marts. In the early 2000s, it was about just integrating the data. And in 2010s, in this decade, people want to access all the data in a very, very fast manner and in an agile manner to get access to it. This is a recent customer example that I worked on myself. So this is an electronics devices manufacturer, and they wanted to do warranty data analysis on the data that was generated out of the factories. So it was a complex multi-structured data. It was a single file which had 8 different CSV formats in there. The volumes were huge. We are talking about several hundred terabytes a year. And for those of you who are familiar with warranty analysis, so the warranty analysis is done over a long period of time. You would like to ideally conduct those tests over 4, 5, 10 years of time, because in the end, you're not looking at the device as a whole, rather than you do warranty analysis on the components. The retention was a problem, and there's big difficulty in correlating all the data sets. So this is an analysis which we have done for most of our customers, and we found out that there is a data access and complexity pattern that resides in all the data sets that our customers work on. So if you look at the total volume, so the Pareto rule applies from the query's access point of view. So most of the time, 80% of your queries are hitting 20% of the data. But if you look at the picture from the other way around, just a very small percentage of your data is complex as well. So most of your complexity also resides in very small amounts of data. And this can be applied to any industry that we are working in. So if you talk about telecommunications, so CDRs and XDRs and the network data are the most, have the highest volume. But they're flat structures, and they change rarely. But if you look at the CRM's data and all those slowly changing dimensions, those are the kind of sources that require complex management. So you need governance and lineage and all those kinds of techniques are required for those kind of structures. So in this case, what we found out was the factory test data had these 8 different data structures in there. So the biggest one was a result data structure. The name of that and it was 95% of the total data volume. And the rest was really master data for all those those details of the repair orders, the test headers, details, logs, and the product sequence numbers. So what we did for during the test was we did the processing transformation of the data inside Hadoop. We stored them all the structures in H catalog tables. Move those 7 tables, those smaller 7 master tables, onto the Teradata side, and used query grid to combine those master tables for adaptive query optimization, which I discussed earlier, to do dynamic correlation of the data sets. And we were able to do fingerprinting of the good devices versus bad, which component is working, which isn't. And we had other additional interesting relational data which we were able to combine, and this was done in less than 2 days' time. Just to end to end, it took us 2 days to build up this solution, and which highlights the point that it was all about agility, and the customer wanted a quick solution out of this technology. So, in summary, as I said, there are different options which Chris has described. So technologies can help you in building this solution if you are using them for the right manner. And if I go back to this particular slide, you would see this pattern would be present in most of your cases. And when you are building solutions, keep this rule in mind, and you would be able to build the right solution. With that, if there are any questions, I'd like to invite Chris back on the stage. Yeah.
Yeah, go ahead.
The query functionality, is it just query that it does, or does it do write back as well? Because there was talk about doing write back from Teradata.
Yes, you can do write back. So the syntax would be similar. So just like you were doing select, you can do insert into my table at Hadoop, select XYZ from another table.
And the return query that you pass through to Hadoop,
yes.
Is it returned in spool or FSG cache?
It is returned in spool.
It's returned in spool. Okay.
Okay, sorry. Isn't it hard for a developer to work with in this case, you have like 2 different languages in one query. What if there will be a third one, and it has to know all these languages? Do you plan to do further with abstraction to have one language? As you can see here, you have a high query, and if you would have more different type of databases, then you will have to know that language as well. Also, you have to know, for each of the database, what kind of data is it, Hadoop or MongoDB, or if I understood this well. So do you plan to kind of make a kind of uniform?
Well, there's a couple of things that happen within this. So a lot of times, so we're showing you how the code works in terms of the syntax underneath. A lot of times when people implement it, what they're doing is they're implementing it as a view within the Teradata environment. So from an end user perspective, what they do is they see a bunch of tables and they see a bunch of data, but they don't really know, well, is this set of data, is that sitting over in Hadoop or is that sitting over in MongoDB? They're just saying, oh, okay, I want to be able to use the SQL syntax that I know, which is Teradata, and join it all together. So right now, the abstraction level is really at that view level. Do you want to add anything, Fawad?
No. In the end, if you want to have so many different technologies connected, to have that single parser which can translate into all these different things, because we are not just talking about databases, we are talking about R grades, R, Python, Ruby, all these things, it becomes extremely complex to have one unified language which can translate into them. So
Yeah, yes, but you use the word virtualization, which is, I mean, this is the goal that I mean,
it's
to have
it's
a
not there. It's
uniform
not there
way
yet.
of-
But as Chris said, the way to achieve it today is to build database views so that it abstracts those that complexity from the end business user, and you can do it that way.
Okay, thank you very much.
Yeah, Mike. Sorry. No, so I got behind you. So I'll
Sorry.
get to you next. Sorry.
What do you do if the underlying data store has schema variant JSON or something like that in it?
So there are some, in the Teradata database, we have complex data types defined as well. So we can actually have JSON types in the Teradata database. We can have XMLs. So if they have those kinds of data types defined, we can extract them as it is, and then parse the JSON type on the Teradata side if the use case demands that. But if there is a complex structure for which there is no automated translation mechanism in the Teradata database, what we would use is the Hadoop SERD concept. So we'll use the serialization format of Hadoop, convert into a relational format before bringing it over to the Teradata system.
In one slide, you showed that to have a very fast data transfer rate, the nodes of the Teradata cluster are talking directly with the nodes of the Hadoop cluster
Yes.
to exchange information in parallel. Now, I found in many enterprises that the Hadoop cluster is shielded from a kind of gateway service because of the different security policies and terms inside the Hadoop cluster. So do you have any blueprint or any ideas how to cope with such a situation?
So
Is
it's
it a need that those nodes need to have a kind of free IP contact to each other?
So it's a very good question, and this is something which we are working with a number of customer deployments. So the way we recommend the deployment of the Hadoop cluster is, if you want performance, you need to have parallel-to-parallel connectivity. All nodes of Teradata need to be able to ping all nodes of Hadoop. There's no other way around it. So what most of our customers do is put both the systems behind a firewall, Teradata and Hadoop, but those systems are able to communicate on an internal link. So each Teradata node has multiple IP interfaces. So some of those interfaces are not available to the external customer LAN the way they are configured. So that communication takes place on the internal LAN, and for Hadoop, using that as a secured manner, so you can block most of its interfaces via the firewall, and for general purpose access, you can have an edge node defined in a DMZ where Nox is installed, and Nox is connecting into doing the reverse proxy thing into the Hadoop cluster and then providing that.
Yeah. So does it mean that the communication between Hadoop and Teradata is going on only one or two ports that I can have a firewall
Yes,
between Teradata and?
yes,
Okay.
yes.
Okay.
Two questions. One is about explain. So because the parser's not parsing that query, it wouldn't do any explain on the subquery.
Yep, yes.
And second question is about security.
Well, just to make a comment, Fawad's correct. It doesn't do a sub-explain on the subquery when you communicate between Teradata and Hadoop. We also have query grid for Teradata to Teradata. So if you have like one of our 6,000 machines for EDW, and let's say one of our 1,000 machines, it will do explain as a subquery against both of those. And so we absolutely are going to, we do that today because it's easier, because we have the same optimizer across the two technologies, but we absolutely want to take that same kind of construct and move it over to Hadoop. But you're right, today it's not. We do that within query grid in a Teradata environment.
That's fine. The last question is around security. So if I'm using LDAP authentication on my Teradata box,
Yep,
and I'm passing this query through my Teradata box to my Hadoop cluster,
yep.
will it pass my credentials or the app Hadoop connection that we define?
Yeah, the credentials would need to have those user password applied there.
Yeah, so that's just tabling DBC, right? The extended DBC to include that.
No, that's not DBC. That's a new database object.
That's a new database object.
So it's called, so the way you create it, create foreign server, Hadoop, username this, server IP this, port this. Yes, yes. Yes, you can pass the credentials. You want automatically without explicitly specifying here? Right now, no.
Okay, any other questions? All right, thank you for your time.
Okay.